In class, we've been performing a whole bunch of different stoichiometry. Stoichiometry is dependent upon understanding the relationship of mole ratios between atoms in a compound and also between compounds in a balanced chemical equation. However, in the laboratory, we're collecting information in units of grams. So in this little lecture, I want to talk about how we can use a gram ratio or a mass ratio to help us figure out the mole ratio of elements in a particular compound. We're going to do this by considering the chemical formula of caffeine that I've given there. If you add it up, this formula weighs 194.22 grams per mole. But let's stop and think about what the numbers in that formula actually mean. They represent a ratio of atoms of a particular element in a compound. So for every one molecule of caffeine, we expect it to have 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens, which is in fact the case, and you can look at that chemical structure on the bottom left. As you also know, it represents a ratio of moles of an element in a compound. So for example, a mole of caffeine molecules would have 8 moles of carbon atoms, and so forth. What this chemical formula does not represent is a ratio of masses. What we can do is take those mole ratios given in the chemical formula and use them to calculate something called the percent composition by mass. And we can do this for each element in a compound. And we'll do it for our target compound here, caffeine. We do this by taking the total mass of one of the elements in that compound divided by the total mass of the compound times 100. So in the case of caffeine, we have carbon, hydrogen, nitrogen, and oxygen. So for carbon, we see that there are 8 carbons in the formula for caffeine, and we multiply that 8 by carbon's molar mass, which is 12.01, and divide by the total mass of the whole caffeine molecule. And we multiply that by 100 to get 49.5%. So what that tells us is just about half of all of the mass of caffeine is contributed by carbon atoms. We can do the same thing for hydrogen. There are 10 hydrogens in caffeine. Each hydrogen contributes a mass of 1.01 gram per mole. Divide by the total mass times 100. And we see that even though there are 10 hydrogens in caffeine, its contribution to the mass is just over 5%. We can carry out the same procedure with nitrogen, where there are 4 nitrogens, and we get about 30% mass contribution, and with oxygen as well. And the oxygens in caffeine contribute about 16% of the total mass. As you might suspect, the mass contributions for each of these elements, when summed, will add to 100. So 100% of the mass of caffeine is represented by these 4 elements. We can also perform these calculations moving in the opposite direction. Because masses are so easily determined in the laboratory, we can actually use those mass percents to determine chemical formulas. The chemical formulas we'll get from these percent composition by mass numbers will give us something called an empirical formula. An empirical formula is defined as the simplest whole number ratio between elements in a compound. So if we think back to our chemical formula for caffeine, which is the real formula, so caffeine does in fact have 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens, you can see that that can be simplified even further by dividing all of those numbers by 2. So for caffeine, we would call the empirical formula C4H5N20. So we'll talk about what that other formula or the real formula is when we get to class, but for now, understand that the empirical formula, the one that we get by this conversion from mass percents to chemical formula, is going to be the simplest whole number ratio. So now let's perform on a different compound the steps that are required to go from mass percents to chemical formula. And again, that will be giving us the empirical formula. So I'm telling you here that the smell of garlic is a result of the molecule allicin. This molecule contains 44.4% carbon, 6.2% hydrogen, 9.9% oxygen, and 39.5% sulfur by mass. So you're getting the information about the composition by mass and being asked to determine the empirical formula. So in step 1, it says if you're given the mass percents, assume that you have a 100-gram sample. So if we think about having a 100-gram sample of this stuff and 44.4% of it is carbon, then 44.4 grams of that 100-gram sample will be carbon. 6.2% or 6.2 grams will be hydrogen. 9.9% or 9.9 grams will be oxygen. And finally, the 39.5% of our 100-gram sample will equate to 39.5 grams of sulfur. So that's step 1. Step 2 is to convert all of these masses to moles of that element. So right now we're getting a mass ratio, but we know a mass ratio is not what's represented in a chemical formula. So if we convert to moles, we'll be able to get closer to getting a mole ratio and getting a chemical formula. So of course, to convert carbon to moles, we divide by its molar mass, and you can see we get 3.7 moles of carbon in this 100-gram sample of allicin. If we convert hydrogen to moles, we get 6.14 moles of hydrogen. Oxygen to moles, we get 0.619 moles of oxygen. And converting to sulfur, we end up with 1.23 moles of sulfur. So these numbers do represent a mole ratio. But as you know from looking at chemical formulas are always listed in whole number ratios. So what we need is a method for getting these mole numbers into whole numbers. And so we do that by going up to step 3 and dividing all of the mole values by the smallest one. So the smallest mole number here is the oxygen, which is 0.619. And so that, of course, gives us a number of 1. And so now we'll divide the rest by 0.619. So if we divide the carbon by 0.619, we get a number of 6. If we divide the hydrogen by 0.619, we get 10. And if we divide sulfur by 0.619, we get 2. And so what we've just done is developed a mole ratio, but because of this dividing, we end up with a whole number mole ratio. And this gives us a chemical formula of 6 carbons, 10 hydrogens, an oxygen, and 2 sulfurs. In the case of allicin, we can look at its chemical formula and we see that it also has 6 carbons, 10 hydrogens, oxygens, and 2 sulfurs. But it is possible, as we saw with caffeine, to have an empirical formula that does not match the real formula. That's something that we'll be dealing with when you arrive to class next time. So make sure you take the quiz, and we'll be continuing this discussion in class.